У нас есть там связанная алгебра. Схема. Но тут, в общем-то, тор, конечно, не супер по делу, потому что, как мы знаем, что это равно и x2, это просто размер с минимальной резольвенты. Из количества минимальных решений раз второго тора. У меня, допустим, f и t переходит в сумму b n и t e n. Так. И t образующий, когда эта вот штука, она точная, в этом вот то точная. Минимальная, то есть, если это d0, d1, то значит d0 содержится в 0. Так, и аналогичное соотношение. Вот эти вот товарищи соотношения, вот n и r, вот n, r и они соотношения, это только тогда, когда композиция равна нулю, это базисные соотношения. Тогда, когда эта вот штука, она точная, и минимальная тогда, когда d это d1 минимальный, то есть его ядро держится во плюс f1. We stated the following theorem last time. If A is greater than connective algebra, K-algebra over some field, then minimal number of algebraic generators is dimension of Tor. No, it's the same thing as dimension of the first term of minimal resolution, so it's the same thing as X, in fact. And minimal number of relations, of algebraic relations, is dimension of the second Tor or the second X between K and K over A. I recall that we have free associative algebra of some generators. Then we have, if we have surjection on our A, surjection of algebras, then images are generators, and kernel is some ideal. And if this ideal in free associative algebra is generated by some elements, then we say that this image of these elements are then these elements are words in Xi are basic relations. This means that any relations, any word in A, which is in this elements which is 0 in A, it must be sum of, it's two-sided ideal, so it's sum of some elements, some words, and our basic relations. And so, how we prove this? We just consider the following sequence. It's K, it's augmentation, all A plus to 0 and K to K. And consider some homomorphism from free module and some another homomorphism from free module. Here, basis goes to AI, and here, Fi goes to some linear combinations. It's from A. And so, theorem follows from the following observations. These elements AI are generators of A if and only if these sequences are exact, is exact. These generators are minimal if and only if this differential is minimal in sense that it's kernel inside of A plus F0. And for relations, if we consider such word in A, Ri, or maybe this word, yes, this word is relation in I if and only if this composition is 0. This is basic relations, it's generators of ideal of relations. If and only if this is exact thing. And it's minimal again if and only if D1 is minimal differential, so its kernel is in A plus F1. If we prove this, we obtain this, because this means that this is the beginning part of minimal resolution, and so dimension of these things are exactly number of generators minimal and minimal relations, and so numbers is the dimension of Tor. Okay? Because I need place to prove this, so I need to clear some of these statements. Okay? Okay, let's start. Okay, let's AI is a generators. AI generators. Then consider. Then I want to check that this is exact. No. Okay. No, of course. No, by definition, my elements by definition are of positive degree because I don't consider unit as one of generator. Okay, I consider associative algebra with unit by assumption. So my elements are of positive degree. So by definition, this composition is 0. So exactness really means that kernel of epsilon is exactly the image. It contains image. Okay, yes. I have that because of my elements AI. No, AI. I in A plus, it's kernel of epsilon. I obtain that image of D0 that's in kernel. Yes, because my basis elements goes to A plus. Okay, so what I really need that if it's generators, then kernel contains an image. Okay, consider some x in kernel. No, it just means that it's of positive dimension. It's an A plus, it's of positive dimension. Because my AI are generators, I can consider it's some sum of some monomials in AI. Some sum of some monomials in AI. Because my x is positive degree, that I know scalar monomial. So in each monomial I can consider I have at least one letter AI, and I can consider this first part of monomial and the leftist letter. Okay. It's because my x is not scalar. Okay. It's because my AI are generators and my x is not scalar. Because it's of course I can consider. For example, I can consider only homogeneous element. My homogeneous element is sum of monomials in AI, and because of it's not scalar, in each monomial I have some letter, and I consider this the leftist letter separately. Okay. No, then by definition, this is image of by A linearity and so on. This is some elements of I. Maybe this is maybe scalar, because maybe if X is AI, then it's AI on unit. Okay, it's okay. So if it's a generator, more or less trivially, that's in image. Okay, opposite direction. Why? If it's exact, then they are generators. So if we know that kernel is image, why AI are generators? No, okay. Где это у меня тут написано? Now here we need some induction on dimension of dimension. So by induction, let me assume that all my in degrees less than n, they generated by my AI. No, I can start from 0, where I have unit automatically, and so I have my base. It's my induction assumption. So a step of induction. So if I have x from an, then it's of positive degree, because in 0 degree I have my unit. So it's from kernel. So x is d0 of some element mi ei. And this is elements of A, and they have less degree than X itself. So by induction, this is monomials in AI. So by induction, this is from degree less than n, because this is of positive degree by homogeneous of multiplication. So by induction, my mi is monomials in AI. And so all my element is monomial in I, so I obtain that any element is monomial in I, so AI are generators, okay? By induction on dimension. Minimality. Minimality is the following observation. It's minimality means that kernel of d0 is in A plus f0. So let d0 of some x is 0. X is some element of our free model f0. It's from f0. No, this means that this is equal to alpha I AI. So if d0 is not minimal, so if there exists some element from kernel which is not from this set, from this set, this means that there exists some element is not from A plus, so scalar maybe. So there exists some scalar. So it's some L I AI plus maybe some others. This is from K. No, this means that we can eliminate, we can express this generator from another, okay, by another generators. This is equality in A. So I have that AI is because this is generators. This is also monomials in my elements ij. In each monomial, I can also express AI from another, and so by induction, I obtain the expression of AI from another ij. Okay. No, again, maybe from induction by dimension. So my number of generators is not minimal if differential is not minimal. No, and conversely, it's more or less the same thing. If my number of generators is not minimal, this means that I can express AI as some monomials of and other things. I can again consider leftist letters, and this is image of D0 mi ei, and this is D0 of ei, and this element ei minus j, mj ej is not 0 in f0, but it's in kernel of my D0. And this is no, this is not from a plus f0 because I have some basis element with scalar coefficient. So it's equivalent to say. Okay. And for relations, more or less the same thing.
Sorry, I have a question. Why here it isn't in A plus multiplied by f0?
No, because f0 is a free module with basis ei. No, we know that ei does not divided by any elements of A. Okay. Except of 0, 1, which is field. It can be divided by field, but not by positive degree elements. Wait. It's because, maybe it's because, yes, it's because our algebra is positively graded. Maybe if it's unpositive, I can consider something like this, maybe. If t of some graded, then maybe, yes, maybe it can be divided. But in our case, ei is basis. It's in some degree, and no, then by definition of our basis, there are no element of positive degree which divide our basic element. No, maybe. No, yes, it's more or less by definition of basis. No, because, no, yes. Okay. Так. For relations, no, more or less the same thing. No, again, if I have d1, d0 is 0, it's equivalent to say that, no, okay, I have d0 of ei is my relation. Yeah. d1 of fi, yes. And no, and composition with d0, it goes to this thing. And so this is 0 if and only if this is relations in my algebra. If it's true in my algebra, okay. So this is equivalent to say that these words are relations. Some relations in my A. It holds in my A. They hold in my A. Okay. Exactness is that it's basic relations. No, again. So if d1 of x is 0. Then, okay, so let these relations, it's Ri. Let Ri are basic relations. Basic relations. I need to check that this follows that x is in image of d0. Okay. Now I have that x is some sum of basis of f1, f some elements of A. So this means that I have some relation of this form. No, of this form, yes. Так, 1 second. D1. No, yes, I have. No, yes, I have in fact this relation in f0. Yes, it's d1. It's d1x. No, it's again it's already 0, but if I apply d0, then I obtain some relation in my A. So I obtain alpha I, bni, ai. It's some relation. So, stop. Что я вообще делаю? Подождите. Не то. So what does it mean? This means that it's kernel, then it's image of d1, because I have d0 to d1, yes. Sorry. It's element from f0, so it's in my elements. Yes, it's some element which is in kernel. So if I apply d0, I obtain some relation. Yes, obtain some relation in my algebra. It's by definition element of kernel. It's some relation. If my relations are basic, then they think by definition of basic relations in two-sided ideal. So it's pk, but ri, rk, qk, and this is, and if we no, because AI are generators, we know this. If we write down these elements as some monomials in AI, then I obtain that in fact, and this is also monomials in AI. By definition of relation, this is equality of words. It's this equality in free associative algebra by definition of basic relations. I have some relation, and this must be in ideal in free associative algebra. So in fact, this equality of words. So in fact, if I in this thing, no, sorry. No, yes, this is also it's a B. What does it mean? B. Where is my definition of Ri? This is Ri. So it's some B and K. Yeah. So this is some monomials in some letters, no, A or X in free associative algebra. It's equality of two words. If I in each monomial consider the last letter and replace it by EI, I obtain the equality in F0. No, because if it's formal equality in words, then if I consider it's in a free module of A, this is also true. If I replace last AI in each word by EI, I obtain the equality in F0. So something like, no, yes, no, again, it's alpha I EI. So here it's PQ, PK, RK, and this is QK, and this is maybe some EK. Now we need to consider two possibilities. If the first, if dimension of QK was positive, then it's 0. Because this equality in F0, it's free basis, it's free module over A. But here, so I consider this as an element in A. But in A, element is 0. This is 0 in A. So this is 0, and I obtain that EI is 0. No, so in fact, my element is 0. Sorry, 1 second. I mean that such summons are 0. So these summons, there are no these summons in my summon. So in fact, these summons are 0, okay, in A. No, because I have this element which is 0. Maybe I have summons where this is had 0 dimension. Sorry, this I consider summons in my sum. If I have summoned with QK was positive degree, then it's 0. If I have summoned of 0 degree, then it was some scalar. And in fact, I replace the last term in this word. So I consider exactly this thing. So this summand gives me something like pk, and here b n k e n. No, and this scalar. This is q. Then this means that qk it's scalar. Lambda k is scalar. So I have this summand. Okay? Do you agree? No, I consider the last letter. If I have some letter here, then I replace it by e, and here is 0 in my a. So I have no such summand. If it was scalar, so last letter is a letter in this equality. It's linear equality. No, so I consider this last letter and replace it by n. So I obtain exactly this thing. So I obtain something like this. But then, no, so if I sum of these summands together, then I obtain that my element x in F0 is sum of such summands where it was 0 dimensional. No, it's something like scalars, pk is some element of a, sum of b and k e n. No, this means that it's sum with some coefficients of these images of, by definition, it's images of d1. So it's d1 of lk, pk, fk. So it's an image. Okay. So if I have basic relations, then my kernel of d0 in image of d1. So it's exact sequence. No, and conversely, if I have exactness, why it's basic relations, so it's more or less. No, yes, it's maybe easier, because if it's exact, no, it needs some induction on dimension. Do you agree? Do you have any questions? Okay. Now, if kernel of d0 is image of d1, why Ri is basic relations. So why any relation can be expressed as something like this with my relations. Okay, let me have some relation. Some word of monomials of A is 0 in my A. Now again, of course, because my generators are minimal, I have no scalar element in my relation. So I have last letters, and I consider these letters. So yes, it's image. It's image of MI in kernel. Sorry, in image. Sorry. Yes, in image. And this is 0. So this element in kernel of D0, so it's an image of D1. So in fact, I obtain that MIEI is D1 of something. No, of something, I don't know. Pn Rn. Sorry. Fn. This means that in F0, I have this equality. MIEI, it's En Rn. No, where again Rn is something like this. Yes. Because my model is free, I know that coefficients are equal, so Mi is sum of Pn Bni. But no, okay. This is equal in A. it's not finished because no, in fact it's kind of converse opposite direction. In the previous argument, I have, if it's basic relation, I have equality in associative algebra, free associative algebra, equality of words, and then of course from this I obtain equality in free module. But here I only have equality in free module. It's no, in general it's much weaker than equality in free associative algebra. So I have this equality in A, but this is not equality of words. In fact, it's equality in A. But here I can use induction of dimension. This equality has less dimension than the previous one. So by induction on dimension, I can assume that in less dimensions, all my relations in A follows from relations of this sort, Ri. So this relation has strictly less dimension than this relation, because dimension of these elements are less than dimension of this element. So this is a relation of less dimension, and so by induction, this relation follows from Rj, which I have. Now then, if this relation follows then from Rj, and this relation, and from this relation, of course, follows this relation. So I obtain that this relation follows from Rj.
Sorry, I misunderstood. Can you repeat please what is Rn and why we can write that sum of m8 multiplied by 8 is equal to sum with n and Rn?
I have d1, fj is basis of f1. It goes to some expression. It's just image of d1. So yes, so it's by definition it's d1 of something. It's the same thing. Because it's free modules, I have equality of coefficients. And this equality of coefficients is some relation in A of less dimension. And by induction, I may assume that this relation follows from my relations. Yes. And so of my relations of less dimension. And from this equality in A and from my relations of this degree, I obtain this relation. Okay? Because I know that this relation is true in A also.
And we proved that rate is basis,
yeah? Yes. So if by dimension I know that my relations are basic in less dimension, then from this I obtain that any relation can be obtained from less dimension and from my relations in my degree now. Because if I know that this relation, then from this relation I obtain this relation. Because if I multiply by AI and apply d0, I obtain 0. Because if I know that this relation is true, then I go conversely. I obtain this element. Yes, I obtain this element, apply d0, and I obtain this element. Here it's my relations Rn. So I obtain Pn Rn. If I know this is true, this is 0, then this is 0. So if I know this relation follows from Rj, and if I know Rn, then I obtain this relation. So this relation follows from Rj and from Rn here. No, it's of degree. It's of some degree, and this is of strictly small degree. No, this is also of strictly small degree, but maybe this is some scalar here, and then it's exactly of my degree. And then it may be some new relations in my degree, but I know them. Okay? And minimality exactly similarly. If it's not minimal, then you can express one relation from another and vice versa. So minimality, it's absolutely similar. So we obtain that minimal set of generators correspond to first minimal resolution module, and minimal set of generators corresponds to second minimal resolution module. So they correspond to dimension of torrent or X between K and K. Okay. no, for example, it was proved by Wall. Wall is topology, so it correspond this. They correspond this question with respect to the standard algebra. He studies standard algebra. It's some graded algebra, and he wanted to know how many you need generators and relations, Adam relations, and he compute some Tor and obtained that you have some bounds on generators and relations, something like this. It was for standard algebra. Okay. Now let's what I want to compute. I want to compute global dimension of my ring of polynomials. No, of course it's n, but I need to compute this. So we need some minimal resolution of polynomial algebra. No, it's so-called Koszul resolution. So we can construct it generally. So let me, for a second, consider a more general situation. So, for example, let R is a commutative ring, and xi is some element, x is some element of R. Then I have such chain complex multiplication by R by x. No, chain complex of length 2 is just any gomorphism. Now I have gomorphism multiplication by x. It's a chain complex of R modules. Now let me define this by kx, denoted by kx. It's a Koszul complex of element x. What is homologies? Or maybe maybe cohomologies. So it will be -1 and this will be 0. What's homology of this complex? What is zero homology? Huh?
R by x.
Yes, R by x. It's co-kernel and -1 homology. No, it's no, yes, it's kind of x torsion or annulator of x, yes, or x torsion of R. Okay. Unless we have some cochain complex, I want to consider the tensor product with this kx. Chain complex over R. It's over R. In fact, this is kind of no. In fact, you can check that this is the same as con. You have multiplication by x in your chain complex, because it's chain complex of R module. This is morphism of complexes, because your differentials are gomorphisms. And you, for any gomorphism of complex, you can consider its cone. Or maybe I did not say what is it. Oh, I said that. I think I said very, very far before. But maybe no. Okay, no. It's no. Okay, it's this thing. It's no. It's not very important. It's by definition this thing. It's what I need. What I want to say that I have a short sequence of chain complex. I have inclusion of my chain complex to this tensor product. No, because no. What is it? What is this? C kx n. I have Cn on 0, so it's Cn, or Cn plus 1 or minus 1. So it's Cn plus Cn plus 1, no, with some differential with Leibniz rule. So in fact I have, no, maybe we can say what is differential, yes? Differential of the first one it's differential of Cn on unit of 0 dimension, yes? So it's dc plus, no, plus minus 1 n c on, oh, maybe better, yes, from the right. Let me multiply from the right. It's without signs in this formula. Yes, maybe it's better. Not because of signs in differentials only. It's the same thing. But now I have.
Why do we have Cn plus? Why do we have?
No, because it's kx0 on Cn plus kx minus 1 on Cn plus 1 plus all others, but I have no other dimensions.
Yes.
So d1, if I have 0 in one dimension, is 0 dimension and n, then I have, what is differential in 0 dimension? Oh, it's 0. So it's 0, then it's 0 dimensional, so I have no sign here, and this is just dc. But if I consider d1 and minus 1 in Cn plus 1, differential of unit in minus 1 is multiplication by x. So I have multiplication by x c, and then minus, and 1 dc. So if I have tensor product over R, so in fact I have something like this. And if I identify one c with c in this identification, so I obtain that in this module, in this chain complex, my differential x as follows: c is in this one is this one is 0, 0, 1, so it goes to c, and c prime is this one, it goes to
Let's go to DC.
yes, you're right, sorry, dc, and this goes to x c prime minus dc prime. Yes. No, sorry. Значит, here it must be of dimension n. It's dimension plus 2. So this is n plus 2. This is of dimension minus 1. It's n plus 2. And this is of the dimension 0. So in fact, it goes to, yes, xc, and here n plus 2. No, yes, and something like, yes, I think something like this. Here, no, it's weird.
Maybe x multiplied by c prime.
C prime, but it's also weird. Okay, C0 goes to, C0 is this one. So it goes to, it's 0. So it goes to dc0, yes? N plus 1, no? And 1. 0 c prime goes to, it's c prime on unit with minus 1. It goes to minus 1 unit. Sorry, what? Yeah, here it's minus 1 unit, of course. So, yes, it goes to yes. Or not. No, it's minus 1. Here is 0 unit. Whoa. Because it was 0 unit multiplied by x. And now it's 0. Sorry. Now it's, yes, it goes to x c prime minus d c prime. What? And now, so differential goes c prime goes to dc plus xc prime dc prime minus dc prime. Okay, well, something like this. This is okay. And so I have inclusion of my cochain complex to my tensor product, where in the dimension n, C goes to C0. Then it's it's a map of chain complex, because it is 0, then this is 0, and this is the same differential, okay? This inclusion of chain complex. Its quotient, what's the quotient of this chain complex? No, if I quote by Cn, I obtain just Cn plus 1. Again, if I forgot all these things, I obtain Cn plus 1 with minus d. It's so-called suspension of C prime. It's shift with minus on differential. So I have this short sequence. No, it's the same thing, it's the same construction as cone. For any homomorphism, if you consider this homomorphism here, it's definition of cone of chain complex, of chain map, chain complex. Okay. So, no, you can, if you don't believe, you can check that this is short sequence. And I obtained long sequence in homologies, okay? In cohomologies. Okay? Do you agree? Do you believe this? So, for any chain complex, I obtain a long sequence in cohomology. So, I have cohomology of C goes to cohomology of X tensor C. Goes to cohomology of shift, it's E plus 1 cohomology of C. Or yes. I suppose yes. Yes. And then goes to E plus 1 C again. And you can check from this definition that a boundary map, it's what's exercised for any cone, for any morphism. Boundary map of this short sequence, it's exactly this map on cohomology. So this is exactly multiplication by x. And so on. It was exercised that if you have map of two chain complex, then you can consider this thing. It's Cn plus Dn plus 1. With this differential, CD goes to dc plus fd minus d. No, dd. Okay, it's u. And you have short sequence. C goes to cone, goes to. Stop. No, it's cohomology. In general, I have that the opposite direction. I have Cu minus du dc plus fu. Так. Yes, and I have inclusion of u. No, here u and c equal 1, so it's not important. But no, in general, if they are different, then I have inclusion of u. Yes, and I have the suspension c. And so this is a short sequence, and you have long sequence in homologies, and in homologies, boundary map is exactly which this induced homologies on homologies by f. It's an exercise what in these formulas. So this is exactly the same thing. No, anyway, we have this long sequence, and so we know that this is x. Okay, so corollary of this thing. Yes. Fc e plus 1 ec. Now, for example, if x is the invertible element of my R, then the multiplication by x is isomorphism always, and homology also is isomorphism because it's multiplication by x minus 1. It's isomorphism. So I obtain that this is acyclic. This is acyclic chain complex. Okay. No, this is trivial case. Non-trivial case, it's when x is a non-zero divisor. Non-zero divisor. Maybe not in R, in cohomology. Cohomology of C. This means that this map is injective. Yes? It's not zero divisor. So this map is injective. And so, and we obtain that cohomology. No, we obtain short acting sequences where it's image of multiplication. It's co-kernel of multiplication, sorry. So we obtain that cohomology of this thing. It's cohomology of C modulo x. No, modulo x. It's co-kernel of multiplication.
Why if x is divisor, then this map is injective?
If x is not non-zero divisor, of course. If it's not non-zero divisor, then this is injective. So we obtain short exact sequences, multiplication by x, hi. No, so this is co-kernel of multiplication by x. This is what I said. No, this is injective, so in fact I have this to 0. Here I have multiplication by x from a minus I, c. And so this is also 0. So this is short exact sequences. And this cohomology is co-kernel of multiplication by x in cohomology of C. Okay?
And why this is injective?
It's by definition. If it's not 0 in cohomology. If it's not zero divisor in cohomology, then it's injective, yes. In cohomology, of course, in cohomology. So, okay. Now you can go inductively. I recall that cohomology of k itself, of kx itself, it's annulator x if it's -1 and r modulo x if it's 0. So let's assume that x is non-zero divisor in R. X is non-zero divisor in R, so this is 0. So I have only non-zero cohomology of my kx itself in 0 dimension. Now then, let's consider R modulo x, its cohomology of my kx. Let me have some element from R such that multiplication on y is such that y is non-zero divisor in R modulo x. So, such that it's non-zero divisor in R modulo x. Then cohomology of ky kx. What is it? It's cohomology of kx modulo y. It's Rx modulo y Rx. No, it's the same thing as R modulo yx. And so on. So now we have a definition. The ordered sequence of elements x1, xn is called regular sequence. Regular sequence in R if xi is not non-zero divisor in quotient by the previous ones. Or maybe infinite. And so in this situation we obtain that cohomology of tensor product of all elementary Koszul complex is non-zero only if it's a quotient. If star is 0 and 0 else. This is called Koszul complex of regular sequence. In fact, no, if you consider on this complex, no, it concentrated in non-negative degrees because it's tensor product of complexes in non-negative degrees. And in 0 degree, it's tensor product of R, so it's R itself. And it has cohomology R modulo xn. This means that if I have this chain complex at 0, and cohomology in this, it's then R 0, and cohomology at this place is R modulo x1 xn. Now this means that what's cohomology at this place? It's this R modulo ideal. So image is exactly this ideal. What I want to say is that if I consider, if I add this 0 cohomology, I obtain exact sequence. So this is kind of augmented Koszul complex. So in fact, yes, and of course, by definition, all in each degree, it's direct sum of tensor products of R and R. It's a direct sum of R. It's free modules. So in general, if x1 xn regular sequence, then we obtain that Koszul complex is free resolution of quotient. Now I want to say the following thing. I want to say that in fact, Koszul complex can be identified with without this augmentation. What's this Koszul complex? Koszul complex itself can be identified with exterior algebra over R of some of n elements in degree -1 as differential graded algebra. So I have multiplication as exterior algebra, and differential satisfying Leibniz rule, and then if I apply this differential on, so if my differential satisfies Leibniz rule, it's enough to define my differential on generators, and on UI it's xi. I means that this is of 0 dimension. It lies in R. This is in -1 dimension. Zero dimension of exterior algebra is R itself, and this is elements of my R elements. Now, for example, it's x1 u2 minus x2 u. Is it obvious? No. Let me just say that this first complex is isomorphic to LU, because I have what is LU? I have R in dimension 0, in dimension -1 with generator unit, and my differential sends this generator to X. It's multiplication by X, so it's isomorphic to my elementary chain complex. And when I consider tensor product of chain complex, tensor product of this algebras is the same algebra. In each dimension, to obtain free summand R, you need choose some -1 summands in some indexes, and this is exterior monomial. Okay. This is because it's true for this thing, and then you can check that tensor product of two exterior algebras with these differentials is the exterior algebra with the same differentials. Okay. So in fact, my Koszul algebra is this has multiplication. It's kind of this differential graded algebra. So for a regular sequence, I obtained this is Koszul resolution, Koszul algebra. no kind of yes, Q, which is resolution of my quotient. This is it's a free resolution in cohomological negative degrees. Yes. Okay, this is clear. So I clear the board. Okay. For example, consider. Give me example of regular sequence of length n. What's an example of regular sequence of length n? Yes, well, for example, of course, yes. So what variables of polynomial ring? It's a regular sequence, of course, because quotient by it's also polynomial. In the next variable, it's non-zero divisor in polynomial ring. So it's our the elementary and the most important case, the most important. Как это? Что я хотел по-русски сказать? Most important example of regular sequence. Regular sequence. No, here it's over any ring. So we obtain this Koszul resolution. Let me another thing. What here it's Koszul, it's extra algebra over R. Now my R, okay, let me denote this K because this is R. But now K is what I want to say now. It's not important that it's field. It's maybe a commutative ring. Okay, and this is K and this is R. So what is R of U? If it's extra algebra over polynomials, I want to say that this is the same thing as polynomial extra algebra over ground ring. No tensor with polynomials with R. So in fact, I have this thing. And this is resolution of R modulo all this regular sequence, so it's K itself. It's a resolution of K over polynomial. So Koszul resolution is a free resolution of K over polynomial ring. Differential, as I said before, it's since ui to xi. Ui has dimension -1. Xi, let me say that it's okay. This is. Let me define b degree in this algebra because I have degree in these variables and degree in these variables. No, as I said before, we didn't consider gradient in this algebra. This is also this was only gradients in these variables. But now I want to maybe define degrees in these variables also for the future, because in the future we will consider graded rings. So I can define, for example, it's not maybe important, but I can define, okay, then b degree of ui is -1, 0, and b degree of xy is 0, 2 because my algebra is commutative. So to say this is a graded commutative, it must be evenly graded. So yes, this is differential, and this differential is it's linear over polynomials. If we have Leibniz rule, linearity of differential is the same thing as this is constant. So it's the same thing that d of this thing is 0. Okay. Вот. It's over K. So I have also got b degree. We can write down the formula for differential. It's just Leibniz rule for these things. It's not very interesting. If you have some thing, yes, and some polynomial, then it's sum minus S, you eliminate S thing and add X, E, S to F. No, this limits rule. Yes, okay. Consider, but on this, this is big-graded differential algebra. This is big-graded algebra, and we have one differential. This differential of b degree 1, 0. It increase degree in UI and no, sorry, and it's degree of what? It's degree of 1. It sends minus 1, 0 to 0, 2. In fact, so it's in of degree 1. Okay. I have another differential on this algebra. It's the RAM differential. So in fact, you can consider this algebra as a differential, algebraic differential forms on affine space. It's function on affine space. This is differential forms. And so you can consider the RAM differential. It's the RAM differential. It's D. It's its differential on this big-graded algebra satisfying Leibniz rule with this property. It sends function xi to differential dxi, which we denote by ui. It's ui. And all differentials are now at to 0. So it's X-ray algebra linear. Any monomial in di, in dxi, it sends to 0. Its new differential it's of degree then -1, -2. Okay. Okay. It's also differential. Because it's differential, no, I can consider. Okay, let me consider the following equality. I have what if I consider d plus d in my algebra. What I obtain? No, it's kind of exercise. You can easily check that if you restrict this thing to this big-graded component LK, tensor, okay. Then on this component it will be multiplication on m plus k. Identity. No, it's easy by definition. It's okay because no, exactly composition is of degree 0 because they are of opposite degrees, and so you on this component, and so it will be identity. So now let's assume that characteristic of our K is now it's a field, and if it's 0, then from this you obtain that in fact, no, if you renormalize the RAM differential in each big-graded component by some divided by some integer numbers, you obtain that D gives you a homotopy, a chain homotopy between 0 and identity. So your Koszul complex, is homotopic to 0. No, with no 0 if you apply if you add this quotient, or homotopic equivalent to this module to quotient module in degree 0. No, because it's resolution, yes. No, if we add this model, then it will be homotopy equivalent to 0. It's a cyclic, and homotopy, in fact, it's not just a cyclic, it's even homotopy equivalent to 0. No, maybe it's an exercise that this is true. What maybe what here? It's augmented Koszul complex with augmentation. Yes, it's resolution and model of which it's resolution. Exercise that it's true over any ring. Over any ring. It's not reported here that Theorem doesn't work, but you can construct another chain homotopy between this augmented Koszul and 0. So in fact, over any ring, it's not just acyclic for regular sequence, but even homotopy equivalent to contractible. But on the other side, you can consider this big-rated algebra as chain complex, augmented, as chain augmented with K, as chain complex with Theorem differential, And now, because Theorem differential is lambda linear, it's also free resolution over external algebra of K also. But now we need to check that this is acyclic. It's contractible by the same argument if characteristic is 0. But now it's important. If characteristic is 0, then this chain complex D is chain homotopy equivalent to 0. Now chain homotopy via Koszul differential. But now it works only for characteristic 0. But if characteristic is 0, it's acyclic complex, and this is free resolution. In fact, it's minimal. It's free lambda resolution of K. No, yes, and in fact, these resolutions are minimal.